So on Wednesday, we continued with section 3.1. I called this part 2, since this is a really long section in your textbook. There's lots of topics to get through and lots of functions that we want to talk about that are useful or at least common in computer science and programming. Last time we talked primarily about the modulus operator and then pseudo-random numbers, which is a way to generate numbers that appear random using a non-random kind of process that a computer can actually do. And we looked at a little snippet of code. And this is actually my copy of the notes, so maybe I should... Oh no, I had switched colors. Okay, we're good. So this is where we were last time, and we will pick up today here with a couple more functions that you should probably know about if you're going to do any sort of computer programming. The next one that we're going to talk about is called the floor function. And the floor of a real number, or if you're programming, this would be something more like a floating point number, denoted this way. So it looks a little bit like an absolute value symbol, except instead of just vertical lines, we put these little feet, I guess you might call them, on the vertical lines. And what this is going to be is the greatest integer less than x, less than the number that we're plugging in. So if we take the floor of, let's just pick something, 3.5, what would we get? Okay, no one's volunteering. So we look for the greatest integer less than 3.5, and that is 3. So it's important to remember that the floor is not the same as rounding, because you always go down. So even if you had a number like, I don't know, 42.9, and you took the floor of your number, be careful with this so that it looks right, it would round down, essentially, to 42. So I think thinking of the floor function as rounding down is a good way to think about it. So you round down to the nearest integer. And if you plug in a whole number, if you actually plug in something like 10, nothing happens to it because you just get, you go down to the greatest integer, less than, and I think I left off a couple words here, less than or equal to your number, then nothing happens, you have the same number. And the next function that we're going to meet is called the ceiling. It's quite similar to the floor, except instead of rounding downwards, you're always going to be rounding upwards. And it also has a similar notation. So before we put kind of little feet on an absolute value symbol, here we're putting those little vertical, we have our vertical lines and then we're putting little horizontal pieces at the top to show that it's a ceiling. So you might imagine we're putting like a ceiling on top of the number, essentially. And this is going to be the least integer greater than, and then again, I dropped a couple words accidentally, greater than or equal to x. So if I try some of these same numbers from before, if I took the ceiling of 3.5, we would go upwards to the least integer greater than 3.5. That would be 4. The ceiling of 42.9. We go upwards to 43. The ceiling of an integer, like 10, would just be the number that you started with, since you're already at an integer, so it's equal to what you started with. And also, if we plug in something like 8.001, even though if we rounded to an integer, this would go down to 8. If we do the ceiling, this would go up to 9, the next integer above 8. Okay. So just like the floor was something like rounding down, the ceiling is essentially rounding up to the nearest integer. Okay, so last time I demonstrated where you could find a few of these functions in a programming language, and I also pulled up this one, these two functions in Python. So last time we looked at the modulus operator and pseudo-random numbers. And now we're just going to take a quick look at floor and ceiling. In Python, which is what I'm using here, the floor and the ceiling functions are contained in a library called math, which contains some common mathematical functions like trig functions, these two, and some other common things like exponentials. But if I take the floor, which is my function, and then I plug in maybe one of the numbers that we've done, 3.5, this should take us to the nearest integer below that, which would be 3. Oops. I need to hit Shift Enter. And I need to actually run this cell. Okay, there we go. So there we go. The floor of 3.5 is 3, and we know that its ceiling is 4. So let's just double check that as well. Good. So both of these functions, the floor and the ceiling functions, you will find, I believe, in almost every programming language, at least all the ones that I'm familiar with, have these functions built in. Okay, let's get rid of this notebook. Unless someone has questions. Anyone have any questions? No? Okay. Before we move on to our next little topic, I do want to spend a second looking at the graphs of the floor and the ceiling function, because they're interesting, because they're quite a bit different from the usual kinds of functions that you might have graphed in your algebra classes or other things that are similar. So let's do the floor first. Just do a little bit of the graph. By hand here. Okay, so let's look over here, and maybe we'll label our x-axis as well. -3, -2, -1. This will be 0, of course, and then 1, 2, 3. And put the same labels on the vertical axis, -3 up to +3. So let's think what would happen if we plugged in a number between -3 and -2 into our floor function. Remember, the floor function is like rounding down. So if we plug in a number between -3 and -2, we're always going to round down to -3. So what we're going to get is something like a flat, a horizontal line segment, something like this. And if I plug in -3, the actual number -3, the floor of that is -3. So I might put in a filled in dot there. But if I plugged in -2 into my floor function, I would get -2. It wouldn't round down because it's already an integer. So I might fill in with an open dot at -2 and then put my closed in dot up here at the -2 level. And if you think about it, this is going to continue. Any number between -2 and -1 is going to round down to -2. And then if I plug in -1 itself, it's going to give me -1 when we put it in the floor function. So I get this pattern of little horizontal line segments something like this. And this would just continue if you kept on going off this way or to the left. So this is a very different kind of function than the lines and the parabolas that you might be used to graphing, because it has this sort of discrete stepping property. So you might call this something like a piecewise function. Oops, can't spell here, piecewise, or discrete, because it has this stepping property. And the floor function is very similar to the ceiling function, of course, which we should also sketch in, except they're kind of the opposites of each other. Let's go ahead and just add all the same labels as before so that our graphs match up pretty well. And we can compare them directly. So let's think what would happen if we plugged in -3 into the ceiling function. Well, of course, we would get -3 since it's a whole number already. We don't have to do any rounding down, or ceiling is rounding up, excuse me. But if we plugged in a number between -3 and -2, like say -2.5, all of those numbers would get rounded up to -2. So I could represent that by putting an open circle here and then a horizontal line segment all the way over to -2. And we know the ceiling of -2 is -2. And this pattern will repeat just like this other one did. If we plug in a number between -2 and -1, its ceiling is always -1. We plug in a number between -1 and 0, its ceiling is always 0, and so on and so forth. And then just finish off our little graph here. Like so. Okay, are there any questions over the floor and ceiling functions. Okay, good. Then let's move on. So those, what was it, 4 or 5 functions are the primary new important functions that I wanted to talk about in this section. Your textbook does go into a few more if you wanted to take a look at them. But what we're going to do is go ahead and move on to a new idea. You might have seen this in an algebra class, but this might be totally new to you. And it's a property of a function f from x to y. And it's a property called 1 to 1. And the technical definition of this says that if for all x1 and x2 in your domain x, if the function values at x1 and x2 equal each other, so if f of x1 is equal to f of x2, then x1 had to be equal to x2. So what this is telling us is that if we plug in different numbers, if we plug in numbers into our function and we get the same output value, then those numbers had to be the same to begin with. Another way of saying this in the contrapositive, an equivalent way, is to say that if this is not true, if if x1 is not equal to x2, then the function values are not equal. F of x1 is not equal to f of x2. So this is just reversing, finding the contrapositive of that. Okay. So let's look at a simple function, or a couple simple functions, these two. Very small functions defined with ordered pairs. And we just want to see if these two are 1 to 1. And I think the best way, or the most visual way of doing this, is to make one of those little arrow charts like we did, I guess, in part 1 of this section. So what I would do is I would make columns for the domain and codomain. And maybe I should specify here that x, the domain for both of these functions, is the set 1, 2, and 3. And the codomain y is the set with a, b, and c. Okay. So for each ordered pair, I'll draw an arrow pointing from the x coordinate to the y coordinate. So we'll get an arrow from 1 to b, an arrow from 2 to c, and then an arrow from 3 up to a. And we should look at this chart and determine that if two function values are the same, then the starting point had to be the same. Or if we start at two different points, then the function values are different. So what do you think? Is this one 1 to 1? Does this match the definition? Not getting any volunteers, I guess that's okay. The answer is that yes, this one is 1 to 1, and we can see it from its chart because each arrow points, each point over here in the codomain has at most one arrow pointing at it. So if you start at two different places here in the domain, then you're going to different places in the codomain. So maybe I'll put a note down here explaining that idea. So a function is one-to-one if at most one arrow points to each element in Y. And this is for these little arrow charts. These work for small functions like this one. Let's make another arrow chart for G. So we have the same domain and codomain. And remember, we have arrows pointing from the input to the output. So we'll have an arrow from 1 to A, an arrow from 2 to B, and then an arrow from 3 to A. So we can see right away that there's a difference between this arrow chart and this one, because there's two arrows pointing at the single element A. If we plug one into the function, we'll get A as an output. If we plug 3 into the function, we'll get A as an output as well. So that means we have two different inputs where the function values are the same. So this is false, because f of 1 is equal to f of 3. Maybe I can write that down. But 1 is definitely not equal to 3. So two different inputs pointed to the same output. Okay, are there any questions over this idea of a one-to-one function at the moment? Okay, so no one's asking any questions, but you might be trying to decipher what this means. And this definition can be a little cumbersome to think about when you first see it. I think the best way to think about a one-to-one function is that if you have different inputs into your function, then your outputs are going to be different as well. Let's do another example with the more usual notation for functions. So here I'm going to have a function from the positive integers to the positive integers, where if I plug something in, f of n is equal to 2n plus 1. And I want to determine if this function is one-to-one. So what I have to do is go back to the definition, and if this is going to be one-to-one, I have to show that if two output values are the same, then the input values were the same as well. So this is actually kind of a proof, if we want to say it's one-to-one, we actually have to prove something. So we're going to assume that two outputs are the same. F of n1 is equal to f of n2. And we have to show that the inputs are the same. And this is actually just a little bit of algebra once we set up the equation, because, well, f of n1 is just this. Maybe let's just set this up. Well, you probably would in your other math classes. So just plug this into the function, 2n1 plus 1. Plug n2 into the function, 2n2 plus 1. And now we can do a little bit of algebra to show that n1 is equal to n2. So subtract 1 from both sides, cancel this off, the plus 1s. So you have a 2n1 left over on the left, and a 2n2 on the right. Now we want to get rid of the 2's, so we'll divide through by 2 on both sides. And finally, we can conclude that we had the same values. N1 is equal to N2. And that's where you can stop. Okay, any questions over that second example there? No questions? Okay, so if there aren't any other questions, let's move right along to the next idea. Another property of functions. This one is called onto. A function f from x to y is onto if for every element y in the codomain, there is an element x in the domain such that f of x is equal, oops, left off a letter, f of x is equal to that element in the codomain. So f of x equals y. Okay, so again, I think it's good to look at some small functions and maybe their arrow diagrams to see if we can decipher what it means for a function to be onto. And this one, we're going to have the same x and y as the example on the previous page. X is the set 1, 2, 3, and the codomain y is the set ABC. Let's make their two arrow diagrams. Okay, maybe add in some labels. So here we need arrows pointing from 1 to A, 2 to C, and then 3 to B. And then for my other my other function, G, we'll make another arrow diagram. Now we'll have an arrow from 1 to B, and an arrow from 2 to A, and then an arrow from 3 to B, like so. So what's the difference between these two arrow diagrams for F and G? Well, the biggest difference that I noticed right away is that every element over here in Y has an arrow pointing to it. And in this function G, we can see that C does not have an arrow pointing at it. So that means there's no input from my set X where the output is equal to C. So that means this first one is actually on 2, and the second one is not on 2. And if we're looking at an arrow diagram, what we're looking for is this. So a function is on 2 if there's at least one arrow pointing to each element in the codomain, Y. Are there any questions over that example with the arrow charts?
Okay. So if there's, okay, say let's say we had a fourth element in X and Y. If the fourth element also went to either A, B, or C, okay, sorry, just X. I don't know why I said Y. So if the fourth element also went to A, B, or C, it's still on 2, right? It just wouldn't be 1-to-1.
Yes, yeah, you're right. So if I had maybe the number 4 added to the set, and we can just draw an arrow somewhere. Yeah, it's still on 2 because there's at least one arrow pointing to each element in Y. That's right. But now it's not 1-to-1 because there's 2 arrows pointing to C. Yeah, that's good. So to wrap up our discussion of on-to functions, let's look at another example where we're looking at the more usual kind of notation, where we're given a rule for our function instead of a set. So here's my function f, and we know f of x is equal to 1 over x squared, and this is from the non-zero real numbers to the positive real numbers, and I want to determine if it's onto. So if we want to say it's onto, we have to solve, or we have to say that there's a solution to this equation for any positive y. So I'm saying for any element, any positive real number, then I can find something to plug in so that this is equal to y. So just like before, it became a little bit of an algebra problem. And in this case, we have to say that there's an x that maps to y, so we have to solve for x. And this is a relatively straightforward little algebra problem. You would want to multiply through on both sides by x squared and divide through by y. So you would say x squared is equal to 1 over y. And then you would take the square root of both sides. To get this as your answer. And really, we should have a plus or minus here, since x can be a negative as long as it's, not 0. And when we take a square, that minus sign will go away. So just like when you have to take square roots in your previous math classes, we do have to worry about this plus or minus thing. And we know that this is allowed, that we're able to take a square root and divide by y, because we know that y is greater than 0. So it's not going to be 0. We don't have to worry about dividing by 0. And we don't have to worry about taking the square root of a negative number. So the square root is okay. So this confirms that if we wanted to map something to y, if we wanted to plug in something and get y as the output, then I have two options to plug in. I can plug in positive 1 over the square root of y, or negative 1 over the square root of y. Okay. And that looks like it's a good stopping point. We're right at the end of class. So I'll go ahead and maybe stop the recording. Oh, and I did want to mention that the reason why you might be worried about something like a one-to-one function in computer science, I know of a really good application, is actually cryptography. If you're trying to encrypt something, you want to make sure that when you're encrypting something, you don't encrypt two different things as the same thing, because you need to be able to reverse your encryption so that you can figure out what you originally had to begin with. So that's one application where a one-to-one function is actually really important.